Right, so our next type of proof, induction, which of course we have seen already. In extension 1, the induction proofs tend to be reasonably straightforward. They're usually one of a specific type. Extension 2, we can have a bit more fun with induction. Recall we've seen the series type. That's where it all started. I've written it in some notation here, but here's one that's of a series type, and the general term there is 4 on r, r plus 1, r plus 2, and we're proposing there that the sum of all the terms in that particular series would be 1 minus 2 on n plus 1, n plus 2. So let's go through our technique, prove it to the first case. Some people call it the base case. So n equals 1. So on the left hand side, subbing into our general term there, we end up with 2/3. Right hand side, we sub it into our proposed formula and we get 2/3. So okay, it works for the first situation. Alright, so in this case, the left hand side does equal the right hand side. Now I'm going to assume it's true for n equals k, where k is a positive integer. So in other words, there's my assumption. Basically, I replace the n with a k. Now we want to prove it true for the next case. Now remember, when you're using sum notation, the general term doesn't change because all of a sudden we've gone to k plus 1. All that changes is the number on the top of the sum. Now is k plus 1 instead of k. The right-hand side will change. So that becomes 1 minus 2 on k plus 2, k plus 3. So proof. Well, if it's a series type, what we tend to do is rewrite as sum to k plus the k plus 1th term. Well, I've put the sum second over there. So there's our sum to k. The k plus 1th term would be 4 on k plus 1, k plus 2, k plus 3. Now, we've assumed that that sum is 1 minus 2 on k plus 1, k plus 2. All right, where are we heading? We want to prove, all right, we've got the 1 minus. I'm not going to touch that. There's no point putting that into the fraction, only to later on pull it back out again. But the two fractions I want to join together, and hopefully we can show that that is 2 on k plus 2, k plus 3. So our common denominator is k plus 1, k plus 2, k plus 3. So the second fraction we have to multiply by k plus 3. Now be very careful, because I even was looking at there, right? And I got a bit confused myself. Be very careful with the negative signs there. So I'm saying minus the whole fraction. So on the top of the fraction, that's still positive 2, but it'll become minus 4 here, which becomes 2 outside of k plus 1. The k plus 1's cancel, and I think that's what we were trying to get, was it? Yeah. Now remember, inside the induction, there is still a deductive proof. That's the actual proof part of the induction is a deductive proof. So we conclude with the if-then statement. And that's why we always write this down. Now, I've sort of gone then if rather than if then, but it's still the same thing. We're saying the result is true for n equals k plus 1 if it is true for n equals k. Then finally we go and induce the solution. And so we know, well, hang on, we proved it was true for n equals 1. So it's got to be true for all integers that are positive by induction. And that's good enough for a conclusion. Here's one from a few years ago now. It's a little bit different. You'll notice we're multiplying the terms together rather than add the terms together. But we can still treat it like a series type. Use the same idea. So the first case is actually n equals 3 in this one, rather than n equals 1. So I'm going to prove true for n equals 3. So 1 minus 2/3 gives us a third. Right hand side, sub it into our formula. Yep, we get 1/3. We've proven it true for our first case. Now, when I do my assumption here, I'm going to add in the fact that our integers are greater than or equal to 3. That may be useful in our proof. I don't know, but it might be. So I'll put it there. So k is going to be an integer such that k is greater than or equal to 3 for this one. So sub in there to show our assumption. We want to prove for k plus 1, and the same sort of idea. As I say, it's still a series type. We're just multiplying instead of adding. So if I put in the kth term there into our multiplication, but our assumption is all those k terms multiplied together. So I can replace that with 2 on k minus 1. Now we're trying to prove Okay, in this case it's all one fraction. So the second part of my multiplication there, I do want to combine into one fraction. So we'll get k plus 1 minus 2, which is of course k minus 1. Cancels with the k minus 1 in the bottom of the first one, and it drops out nicely. There it is. 2 on k, k plus 1. So hence it's true for k plus 1 if it's also true for k, etc., etc., etc. The other type that we looked at last year was divisibility type. So let's do one of those. I'm going to prove that n squared plus 2n is a multiple of 8 if n is an even number. All right. Well, in this case, the first case would be 2 rather than 1, because we're talking about even numbers. So the first case, 2 squared plus 2 times 2, 8. And 8 is certainly a multiple of 8. So that's good. So we know it's true for that first case. I'm going to assume it's true for n equals k, where k is an even number. Another way of doing that, I suppose, is you could say, prove it true for n equals 2k, where k is an integer. And that's another way of saying it's an even number. So k squared plus 2k equals 8p, where p is an element of the integers and k is also even. Prove it for n equals k plus 2. And so there we go. I'm going to prove that k plus 2 all squared plus 2 outside of k plus 2 is equal to 8q, where q is some integer. So k plus 2 squared plus 2k plus 2. I need to get my assumption in there. So I'm going to expand this out. And I should be able to withdraw k squared plus 2k out of that. So that gives me 8, because that's what we want the factor to be, outside of p plus k on 2 plus 1. Now we want that to be an integer. And that's where, back in our assumption, it was important I added in my assumption that k was an even number. Because now I can come back to k on 2. Well, because k is even, I know it's divisible by 2. So k on 2 must be an integer. And I would explain that, as you'll notice there. So I've said, yes, q will equal p plus k on 2 plus 1, which will be an integer because we know k is an even number. Hence the result is true for n equals k plus 2, if it's also true for k, etc., etc. Alright, or, as I mentioned, you might find it easier, and maybe I'll find it easier, for assuming true for n equals 2k, where k is an integer. So thus forcing n to be an even number there. So 4k squared plus 4k is 8p. I'm going to prove it for 2k plus 2 though. So 2k plus 2 squared plus 2k plus 2. Oh, can I expand that one out correct? Let's see. And so we get p plus k plus 1 as the factor, and that certainly is an integer. Hence, etc., etc., etc. All right, now let's have a look at this inequality type. So these are more like what we might see in extension 2. Well, we certainly wouldn't see an inequality one in extension 1. So I'm going to prove 2 to the power of n is always greater than n squared, so long as the integer is greater than 4. So the first case then would be 5. And 2 to the power of 5 is 32. 5 squared is 25. So yes, that works. It's true for 5. Now assume the result's true for n equals k. Again, I'm adding in there that such that k is greater than 4. That might be useful in my proof. So I'm assuming that 2 to the power of k is greater than k squared, and I'm also assuming k is greater than 4. Prove that the result's true for k plus 1. So there we go. Now I'm going to use the idea of moving everything to one side, because I think it's going to be easier to show that this expression is always positive, rather than trying to show the 2 to the power of k plus 1, etc. So I'll start with the left-hand side. Let's expand it out. Now I want to get my assumption in there. So what was my assumption again? It was, there it is, 2 to the power of k is greater than k squared. So therefore this expression must be greater than 2 lots of k squared minus 2k minus 1, which is equal to k squared minus 2k minus 1. Remember, I'm trying to show this is always greater than 0. But remember my other bit of my assumption? Yeah. So actually, I don't need to make it a perfect square, because I know k is greater than 4. Therefore, 4 squared minus 2 times 4 minus 1, it's always got to be bigger than that, which is greater than 0. Hence it's true for k plus 1 if it's true for k. A graph, yes, you certainly can draw a graph. as a way of part of your proof? Definitely. All right, let's try another one. 1 plus 1 on 2 squared, 1 on 3 squared, etc., up to 1 on n squared is always less than or equal to 2 minus 1 on n. Prove the result's true for n equals 1. Well, left-hand side's 1, right-hand side's 1. So yes, it is less than or equal to. Happens to be equal to, but it is less than or equal to. My assumption, okay, make it k. Prove the result's true for k plus 1. Again, I'm going to use the idea. Let's move everything to the left-hand side. This time I'm going to try and show that expression's always negative. So I'll add in the second last term of the series, because that was our assumption. So I can now assume that that is 2 minus 1 on k plus 1 on k plus 1 squared, minus 2 plus 1 on k plus 1. Well, 2 minus 2, that's nice, that goes. And I'll make it all one fraction. Top of the fraction becomes negative 1, because the bottom of the fraction, k plus 1 squared, well, that's positive, k. Well, we've assumed k is a positive integer. So that certainly has to be less than 0. And we know that because k is always greater than 0. Hence, the result is true, etc., etc., etc. Now, this one's different again. I mean, the idea of proof by induction is exactly that. It's an idea. 2 vertical walls and the floor meet at a corner. 1 cubed is placed in the corner, and then a solid shape is formed by placing identical cubes to form horizontal rows on the floor, and then a row, a column, I suppose is a better word really, by stacking it vertically. And there's an example that has 9 cubes. So n is the number of cubes to be used in the shape. We're going to use the idea of induction to show that the number of exposed faces is always 2n plus 1. So we're going to prove it true for n equals 1. In other words, 1 cube. So there's the picture if we had 1 cube. And this is where drawing diagrams certainly can help in our proof. So there's the picture. Now the first cube has 3 exposed faces, if we look at that. So if I sub that into the formula, yes indeed I get 3. So the formula works when there's 1 cube. I'm now going to assume it's true for k cubes. So in other words, we are going to assume that k cubes will have 2k plus 1 exposed faces. And I'm going to prove it true for n equals k plus 1. So we want to prove that k plus 1 cubes will have 2k plus 3 exposed faces. Here's my proof. And I'm doing it with a picture to help. So in the corner there, I'm saying I've got k cubes. And there's my k plus 1 cube that I'm going to add to it. Now, it doesn't really matter where I add it, because of symmetry, it'll result in the same thing. Because I can always turn the picture and get the same thing. So it doesn't matter where I put the cube. I'm going to put it on the end of that row there. Now, what will happen with the addition of the cube? It's going to cover up, and I've shaded it in, it's going to cover up one of the existing faces. So I've lost one of the existing faces. But it will leave 3 faces of the new cube. So I've lost 1 face of the old cubes, but I've added 3 extra faces. So all up, I've added 2 extra faces. Okay, so the number of faces in k plus 1 cubes will be the number in k cubes minus the 1 that I lost of the original cubes, but plus the 3 that I'm adding in, which becomes 2k plus 1 minus 1 plus 3, 2k plus 3. And that's what I wanted to prove. So the use of a picture can sometimes help in these proofs. And since it's true for n equals 1, etc., etc., etc. Induction and recursive formulas. So a recursive formula, remember back when we were looking at series and sequences? It's where you work out the next one based upon previous terms and so on. If your recursive formula is in terms of m preceding terms, then I've got to prove it true for the first m terms. So however many things I'm substituting into the formula. And I'll need to assume it's true then for n equals k, k minus 1, up to whatever k minus n minus 1 is. Note, the recursive formula is given to be true. That's not what you're trying to prove. A lot of people make the mistake of trying to prove the recursive formula. That's given to you. The first term is the square root of 2. The recursive formula is every successive term will be the square root of 2 plus the term before it. And we're going to prove that every term is less than 2. Prove it true for 1. Well, they told me the first term was the square root of 2. Square root of 2 is less than 2. So, yep, that fact is true for n equals 1. We're going to assume the result's true for n equals k. So the kth term will be less than 2. I now want to prove that the k plus 1th term is less than 2. Now, this is where I use the recursive formula. So I'll start with that. They told me that term k plus 1 is the square root of 2 plus term k. And I'll see if I can get my assumption in there. Well, ak is less than 2. So that expression will be less than the square root of 2 plus 2. 2 plus 2 is 4. Square root of 4 is 2. So yes, term k plus 1 is less than 2. Hence the result's true for k plus 1, etc., etc. The classic Fibonacci. And this one's nice. If you recognise the number in the parentheses there, 1 plus the square root of 5 on 2 is the irrational number phi. So in Fibonacci, the classic Fibonacci sequence is that the first term and the second term are both equal to 1. And then you get them by adding the two previous and so on. So let's prove it true. Now I've got to prove it true for 1 and 2 because my recursive formula involves 2 previous terms. So I need to prove it true for the first 2 terms, which is n equals 1 and 2. Well, n equals 1, a1 is 1, and on the right-hand side we get the golden ratio. So rounding off, 1.62. So yes, that one's true. N equals 2. Right-hand side, well, if I square that, I end up actually with 2.6, and so on and so on. So it's certainly true for the second one as well. So now I'll assume it's true for, now it's up to you, I guess, what you make your consecutives. I've gone for k and k plus 1, and I'm going to prove it true for k plus 2. I mean, you could go with k and k minus 1 and prove it true for k plus 1. It's up to you. So I'm going to assume that term k is less than 1 plus root 5 on 2 to the power of k, and term k plus 1 is less than 1 plus root 5 on 2 to the power of k plus 1. We'll now prove it for k plus 2. So I want to prove, and again, I'm moving everything to the left-hand side. I'm going to show this is always negative. Okay, the recursive formula is ak plus 1. Now, we have assumed something about both of those terms. So that's why we needed to make 2 assumptions. So I can substitute into my recursive formula. So I'll get that is less than 1 plus root 5 to the power of k, well, on 2, of course, 1 plus root 5 k plus 1, and then minus 1 plus root 5 k plus 2. We want to show this is always negative. I'm going to pull out the common factor to the power of k as the common factor. So I'm left with 1 plus root 5 on 2 minus 1 plus root 5 on 2 squared. Now I know 1 plus root 5 on 2 to the power of k, that part's greater than 0. So therefore, if I can show the other bit is negative, positive times a negative would be a negative, and I'll be okay. So let's have a look at just that second part. Common denominator would be 4. And tidying up the numerator, eventually, we get that it's actually 0. So I can now say that term k plus 1 minus that fraction is less than 0. So the result is true. A lovely little proof. All right.